This talk is going to be pretty theoretical. I'm going to talk about chaos engineering, and I don't have like cool demos. I think the cool demo part is going to be covered by Kelsey Hightower next. Uh, but this talk is going to be some of the things that um, I have learned over the years while doing distributed systems, while designing distributed systems, while running microservices, and I'm going to be talking about chaos engineering and some of the patterns that can be used for building highly resilient and highly available distributed systems. Background about me: I work at a company called Hashicorp. I work on a distributed cluster scheduler called Nomad. I'm a core contributor to Nomad, and before HashiCorp, I was an engineer in the platform group at Netflix. And before that, I was pretty much like doing distributed systems for various startups and things like that. Pretty much been a platform engineer and a web ops SRE type of a person for most of my career. So this talk is going to be about failure. We are going to be talking about how things fail. It might get depressing at some stage, because as we talk more and more about failures, as we talk more and more about how systems fail in production. But I mean, I kind of like thinking how things fail and thinking like how to design resilient systems. So this topic is very close to my heart. So what does failure means? Failure basically means lack of success, or it basically means this is like what Google shows, right? When you just type define failure, it basically means when we don't get what we expect, or when we see something which is not really expected. And failures are the most common thing in software engineering and in production systems. Like it's pretty much like it's inevitable, right? um, this is like a high level picture of how I see things. Uh, so first is like enterprise IT. So first is like enterprise IT, like very slow changing and very small scale. Maybe like couple of like enterprise apps like on a few boxes, serving like like some amount of users. Uh, the thing about enterprise IT is that I have often seen there are maintenance times and things like that. So they have the liberty of taking time to do scheduled maintenance and periodic maintenance and things like that. And things don't change really much. Like when I used to be a consultant at ThoughtWorks, we were regularly like battling things like deploy once every month or deploy once every week or something like that. So things change very slowly, and when things change slowly, like things fail pretty less. And then there are the telcos like Ericsson and the other telcos of the world, uh, pretty large scale, uh, and changes happen very less. Like you don't hear people changing routers which are in production in a transit somewhere getting changed every other week. The software in them don't change much. Then there are systems like Rline, for example, which are pretty much geared for building systems like that. So the software doesn't change much, but eventually at some stage the hardware gives up, right? At some stage you'll see like packets doing like in like bad checksum, like one packet is like getting corrupted or something like that, and you see like bad issues in the transit. Those are like the situations when failure happens because of hardware. And then there are startups. Startups are places where people need to innovate really fast, people need to pivot really fast. Scale is still small, but changes happen really fast. People are trying to put like things very soon, like as soon as they are done, they want users to experience their products. They don't want a large pile of inventories. So failures happen there, but it's mostly on the software side. Like if you run 100 servers or 200 servers, chances are there your clusters are not going to fail because there are hardware failures, because there are very less amount of hardware. And then there is like the place where we like to play, like web scale stuff, where like where users want to see Breaking Bad the whole time, or people want to deploy changes into production the whole time. So as a platform engineer, like like I work on systems which sort of are the epicenter or the foundational service. Like for example, service discovery or like load balancers. Like if those systems fail, nothing else is going to work. So in those kind of a systems, like we always see that 20-30% of the cluster is always in a failed state. Like literally, like 20-30% of the cluster, if you run like 60-70,000 servers, like they will be like in a failure state. And then like the game is not about how you babysit those services so that those services are always up and running. The game is about how do you not wake up in the middle of the night, like seriously. I mean, I kid you not, like this is what it is all about, how to like make software recover when they have failed. It's all about that. So those are systems which changes very rapidly, and also are pretty large scale, right? Uh, so this in this talk we are going to be focusing on the top right part of the axis. We are going to be talking about situations when things fail because things are changing really fast, and also we are operating at a global scale. When I say global scale, I mean like running across multiple data centers, running tens of thousands of servers, doing 40 or 50 deployments a day, that kind of an environment. So this is this is like one of my favorite quotes from this book, Drift into Failure by Sidney Dekker. It says the explosive growth of software has added greatly to systems interactive complexity. With software, the possible states that a system can end up is becoming mind-boggling. So today we are in the era of writing softwares which are web scale. And what does web scale software means? It pretty much means that we are running software which runs across hundreds of machines in our data center, which are essentially distributed systems, right? And what are distributed systems? Distributed systems are systems which are interacting with like a bunch of different services and then working together to produce the desired outcome. And with systems like that, there are so many touch points that the complexity of how that system is going to work in production is pretty much like unknown at most amount of in like most situations. And we can model and understand each of these in isolation, but when released into competitive, nominally regulated societies, their connections proliferate, their interactions and interdependencies multiply, their complexities mushroom. So what it basically means is that you as a team or like as a microservice developer or like a service developer can do an awesome job. But if all of us were developing 20 or 30 services in this one room, like we would basically see that things can get pretty much out of control like in no time, because of the way software works, because of incidental complexity in software, because of Murphy's law, because things eventually don't work the way like we expect them to work, right? So I'm going to talk about like talk about what we just said with like a example which is sort of like my favorite and something that I used to see pretty often when I was at Netflix. One of the so how do you think like people make websites fast? Like 90% of the times people put caches in front of them, right? Like that's like the empirical way of making anything fast. Like put a cache and then things magically becomes like 20-30 times faster. And like it's pretty much like how things work. um, and So what happens is like you have all these front end servers, right? And they, instead of reading from the origin servers, they read from a cache because the origin servers are doing complex business logics and stuff like that. And if a user is doing the same request over and over again, chances are that the same business logic is going to be applied and we can cache the result. Unless like it's a ticketing website or something like that where we need like more real-time information. If it's something like something which is like a catalog or something which is recomputed only when certain business logic changes, then most of the times we can cache them. So this is an example like that. So in a normal situation, like the number of cache misses are really less, so you are going to be hitting over and over the cache, the same cache again, and so things are really fine and nice, and users are watching their photos and they're relaxing and all is good, you're not getting paged. life is good. Um, but when something is not in the cache, the request obviously goes to the origin, and then your actual servers, which like you people like you and I have written, actually does its work and then returns the data. And when they are returning the data, if it's an actual service, it's probably not going to be returning in like 1 millisecond or 2 milliseconds, right? It's probably touching Postgres, it's probably touching Cassandra, it's probably touching Riak or whatever your favorite data store is, right? It's probably like talking, if it's like a CP system, like a consistent, like if it's highly consistent, it's probably doing Paxos, or it's probably talking to Zookeeper or something like that. And we all know like how Paxos and Zookeeper are in production, right? So most of the times, like, when things go to the origin server, that's when like all the real action happens, right? and and we hit the real servers, right? And we compute the result, and then we return it back to the user, and we also write it to the cache, so that from now on, like, we return the cached result. Now what happens when we lose a cache shard, right? So say we ran some 20 memcache server or 20 Redis server using some consistent hashing scheme, and we lost like one particular shard. That means we lost, like, say, I don't know, like 1/3 or 1/10 of the data. And say that 1/10 of the data was like really hot. In that case, what would happen is we are going to be calling the origin servers. And now in a normal situation, the servers which are doing say 300 RPS, in a situation where they have lost a cache, they will have to do some 10 times the request that it does on a normal time. And what happens when they do not like 10 times more requests? Things don't work really well, because you will probably, like, at some stage, like, there is some bottleneck, right? You're probably running your data store which can do n RPS, and if on a normal basis it is not doing like 10 times of 300 RPS, 90% of the chances that it's going to break in the middle of the night, if this happens in the middle of the night, right? Or whenever it happens. So we see that when the origin servers get overloaded, the front end servers get overloaded too, because they are not getting the data that they need, and people won't get the results that they are expecting. So caches are good, and we use caches for making performant web services, but then they become an availability concern, right? So this is an example, right? There will be like similar examples in like other areas as well. Like, think about think about highly consistent systems. So people say that eventually consistent systems like Cassandra or React, like, are hard to reason about, because we don't know like when the data is going to converge. Whereas like a consistent systems which has, say, ACID guarantees or something like that, are more reasonable, or more easier to understand, because we know that there is a transaction going on, and when there is a transaction, when the transaction ends, like, the world is going to come into a consistent state. But with more consistency and more clear boundaries of the system, like, or most softwares take like an availability hit, because there is always going to be a situation when things are not going to be consistent, when there is going to be a fault in the network, for example, right? So has anyone run like MySQL servers in production and had a bad day because there was like a lag in replica servers? Anyone? Okay, I see like a few hands, right? So like, it's like really nice and everything, but when there is replication lags because of network latency and stuff, like, things don't work really well, and we see like issues in our software stack. So there are like all these problems. So what I'm trying to say is that we must think about resiliency when we are writing software, right? Like, systems are going to be failing, and we need to be thinking about how systems are failing when designing the system, and not as an afterthought. It's not the responsibility of the sysadmin or the SRE to babysit the software that a developer has written, right? We need to be working together in terms of thinking how systems are going to be failing, and working towards like an architecture that's going to be promoting resiliency right from the get-go. So we all love microservices. They are a thing these days, and like, it makes sense to to bisect like a whole big monolithic system into bunch of microservices. So this is like how it looks. You get a user request, and then the user request fans out to multiple dependencies, So this is all good and nice, but we see that catastrophic, we know that again, like something from another paper that I like, how complex systems fail. The paper says that over catastrophic failure occurs when small apparently innocuous failure joins to create opportunity for a systemic accident. What it basically means in plain, like in simpler words, is that when failure happens, it's almost like a thundering herd. So say for example, out of all this dependency, there was like this dependency I which failed, but everything else is working. And this was like a Tomcat web server fronting all this microservices, which is getting the user request, and this one particular service is failing. Like what would happen is, at some stage, the threads which are calling that dependency I is going to like get blocked. And as the threads keep getting blocked, like the end user requests are going to keep piling up. And at some stage, Tomcat, which is at the edge, is going to like give up. It's not going to, like respond to any request, even though we saw that there were like all the other services in the whole graph was working really well. So this particular phenomena is called, in distributed systems, it's pretty much like very common. It's known as like the thundering herd syndrome. So when like one system fails, like in distributed systems, we see that everything else fails. Like there is a cascading effect of failures, right? It's almost like you have a pile of cards, you topple the first one and then the rest of the cards fall down. So even if like something which is like really which is really innocent, like we need to be protecting everything in our whole network. The whole design, the whole architecture has to be seen holistically. So these are some of the things that like that sort of has like helped in the past about with 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 respect to like building resilient systems, is like smart load balancers. The thing with smart load balancers is that most of the times, like dependencies like this, like if they are microservices, like they're not running on a single server. They are probably running like on 200 servers or 100 servers or 150 servers, like depending on your scale, right? With smart load balancers, like you can have load balancing schemes where you choose from the group of servers which are doing well at a given point of time. And if a server is not doing well, you basically take it out of the list of load balancers and then you move them around and things like that. There are like lots of advanced load balancing strategies where you do like random shuffle, for example. Like for example, HAProxy and Nginx and things like that, like if you have 150 servers, it will do like round robin or like random amongst all the 150 servers. But you could do like smarter stuff, like pick 8 and then load balance across 8. And then across your fleet, you can do like, you can randomize the set of servers that you want to pick for doing load balancing. So so what it means is that the more there is randomness, the more better systems perform. That's what like we have seen in production. Like so between systems not working and systems working really well, there is always a factor of randomness. Like failures happen randomly, but we have also seen that when you inject randomness into the system of when it works really well, the system keeps working really well. And then circuit breakers. So I don't have a diagram for circuit breakers. What it means is that if there is a dependency I which is like failing, like instead of calling to the real dependency, we can like throw a fallback response. We trip the circuit and then we never call the dependency I. In that case, like we avoid this entire dependency by giving like a cached response or a default response or something like that. If you are in the Java land, there is a library that we wrote at Netflix. It was called Hystrix. Hystrix is a Java library which implements the circuit breaker pattern. I recommend reading that, reading the README of Hystrix. It's pretty nicely done. And then dynamic cluster scheduler. So what dynamic cluster schedulers does is that if you have hardware failures, if you have like network failures, with dynamic cluster schedulers, you can move your software around your data center and you can land your software on a host which is healthy, for example. So we often used to see that when we ran servers on AWS, after 30-35 days, the Docker daemon used to give up because of memory leaks and things like that. So when we had like dynamic cluster schedulers, like we could like basically like nuke a machine when that machine is not working well, and then move all the software that was running on that machine onto onto another healthy machine on containers. So we are going to be talking more about cluster schedulers tomorrow, so I'm going to skip that part. Um, come to my talk tomorrow, um, and we'll discuss about dynamic cluster scheduler in depth. And then dynamic service discovery in distributed systems, we end up using like Zookeeper or Console or etcd or something like that, right? We need to know what are the catalog of our services. So with dynamic service discovery, what it means is that, like, when there is a failure in a service or in a particular shard of a service, the service discovery system should take that thing out of the picture. If the service discovery doesn't advertise about a service which is in a failed state, there is no question of us talking to that failed service. And the more the minute resolution the service discovery system has, the better it is for resiliency. And continuous failure injection. So what continuous failure injection means is, continuous failure injection is in the realm of chaos engineering that I was talking about. So what it means is that we know that systems fail in production. We know that at some stage the healthy system that is running is going to fail in some unexpected way. Now, how about we change the game? We introduce, instead of waiting for the failure to happen randomly, we inject random failures into the system, and not in the middle of the night, but at 10 a.m. in the morning, right? So when we introduce random failures during our business hours and we see how the system is failing, then we can fix the software to handle those random failures that we have injected, right? So what it means is that we are reducing the chances of randomness, we are reducing the chances of the undeterministic behavior of our systems when they are unsupervised. Does it make sense? Feel free to stop me. And like, so again, like, this is something that we used to do very often at Netflix. There was this thing called Chaos Monkey. We had Simian army. So what we used to do is, like, we used to just like run Simian, throw like a bunch of monkeys on our servers, kill servers, introduce network latencies, and see like how things broke. And when things broke, we knew that this is how things might actually break in production someday. And that we would do those exercises for like 5 minutes or 7 minutes or 10 minutes, right? It's not like injecting failures for the whole day. We don't want to do that, right? We want to inject failures for 5 minutes, make like 1 or 2% of our users suffer, right? Not like so many users, not allow so many users to suffer those that, like, on social media we get like bad PR, but do it in a controlled fashion, right? So that's pretty much like what chaos engineering is all about. So what does it mean? What does chaos mean? Chaos means that you understand what the steady state is, right? We are all really good at understanding what steady state is because we are designing for steady state. We are never designing for non-steady state, right? And then we create like two clusters. Like, it basically says control group and experimental group. It's basically like creating two clusters. Put one cluster through like the chaos, put the chaos exercise on it, like put some network latency or nuke the database or nuke the cache cluster for one of the clusters, right? And have your smart load balancer move say 1% of the traffic or 2% of the traffic there, right? And then see how things break compared to the other system which is running in steady state. And then compare those two systems and then fix the one which was in the experimental state to behave as if it was in the steady state, even when like the database was broken or the cache was broken. And when you achieve that, like, that's like the nirvana of resilient systems. It chaos takes a lot of time. I've seen like a lot of people running chaos in test first and then in production. But the day you run chaos in production is that's the day when, like, you would know that your software is truly designed for any kind of outage. Sorry, these slides are not nicely done. I literally did it like after I came here, reached Oslo. So basically, the last 2 points are that I want us to drive home is resiliency is by design, and failure inevitably happens in production systems. That's pretty much it from me. Questions?